Hi guys. Focus of this call is writing EVM bytecode. So EVM is Ethereum virtual machine, and just like any virtual machine, हमने फर्स्ट सेमेस्टर में भी स्टडी किया था वर्चुअल मशीन्स के बारे में. जैसे ट्यूरिंग कंप्लीट मशीन है तो उसमें स्टैक होता है, मेमोरी होती है, एंड इट रन्स सम इंस्ट्रक्शंस. So yeah, EVM machine is basically EVM is just a machine like that, and it has some components. So आज we will have a quick discussion about how it works and how to write some basic code, and then finally we will see how Solidity is a language which compiles into this bytecode, and how it helps to write code. Basically मतलब normal लोग EVM bytecode क्यों नहीं लिखते हैं, why they write Solidity code. I mean, it's obvious if you want to write complicated code, then you can write it in a language which is easy to write, and then it compiles into a bytecode which runs on the machine, which machine can understand. So we will start with getting a quick overview of what this EVM Ethereum virtual machine is. So I'm just sharing my screen. By the way, am I audible?
Yeah, you are audible.
Okay. So in the first link, there is a quick explainer on what Ethereum virtual machine is, and you can just go through it. I'll just show some main components of it. So like it has a memory and stack. There is one diagram over here. So in the in Ethereum blockchain, so there are lots of nodes, and people send transactions to it, and the transactions are executed in this Ethereum virtual machine. So Ethereum virtual machine is a small component of the Ethereum blockchain, small and important component of the Ethereum blockchain. There are other components as well, but this is the component that does the state transitions and calculations of uh, what is correct and what is wrong. So in our first semester, the machines that we have studied, it had a tape in which we had a program counter. So program counter is basically you have one strip of instructions. So where are you at? So imagine you have a 100 length 100 characters of instructions. So you are at the first position. So the program counter will say that 0. So you are at the 0th position. And similarly, you are executing the instructions, and you are now at the 10th instruction, 10th character. So the program counter, it's just a number, and it will say that it's 10. So it's at the 10th position in the program or on the strip. So now the machine also has a stack. So you must be familiar with the stack. So you can just push things into it, and pop things into from it, and then memory. So the Ethereum virtual machine has infinite memory. I mean, you cannot use infinite memory, but there is no such limit to the memory. So yeah, some basic things which you can do with on this machine is, if you want to add two numbers, then you can push two numbers on the stack. So for example, push 3, push 4. So now the stack has two numbers, 3 and 4, and now you can just I mean, you should have uh, the program counter on an add instruction. Sorry. So then the add instruction will eat these two two elements on the stack and push back a new element on the stack. That is the output of the add opcode, and 3 plus 4 is 7. So it will take out these two elements from the stack and put 7 in the stack. So this is one element, and then memory is another element. Just a second. Yeah, so we just saw stack, and then so stack is a limited thing in Ethereum virtual machine. It has some depth of 1024 something. I'm not sure if it's mentioned here, but it's mentioned in the yellow paper. I'm not sure about the limit, but it's something like 1024. So that is the depth. So if you keep on pushing uh, elements into the stack, then there will be a limit. You can push more. And also, one important thing I didn't mention, Ethereum virtual machine is a 256-bit machine. So one word size is 256 bits or 32 bytes. So just like our machine, most probably you would be having a laptop which is 64-bit. So, so if a processor is 64-bit, it means that the word size is 64 bits. Previously, a decade ago, we had 32-bit processors, so the word size was 32-bit. But the Ethereum virtual machine is having 256-bit 256-bit word size. So the reason for that is just to work with the keys and hashes easily. Otherwise, it is simulated if it's run on a laptop. So it is just simulating the 256 bits on a 64 bits machine on a hardware level. But anyways, so all the elements on the stack are 256-bit elements. So you can push 1024 uh, 256 bits elements, and in memory, so you have an endless stream of memory which you can write to. So there are some methods which help to write to the memory and read from the memory. So at a time you can read 256 bits and basically read the memory and push on the stack. Or if you have something on the stack, then you can write to memory. So stack is cheap. You can work with the stack very easily. Uh, very easily, I mean, with spending less gas. So there's this gas thing here, which you can think of like petrol. So you're just doing things, and eventually, if this becomes zero, then the machine will stop. It will not execute the further instructions. So this when the execution starts, so there is one huge number provided here, and as you keep on running your program counter executing instructions, eventually this number will if it becomes zero, or if it becomes negative actually, then this will stop, the execution will stop. So you have a stack, you have memory, and then you have this thing called storage. So the stack and memory is an ephemeral storage. So while the execution is going on, this will be retained, but once the execution is done, then this will be deleted. But then the storage is something which will stay even for the next transactions. So basically, you are sending a transaction. You are buying some tokens from the decentralized exchange. So you will send a transaction which will execute a code, and that code will have these stacks and memories temporarily. So the calculation, how much tokens you should get or how much you should pay, it will be done on the stack and memory, and then it will be deleted later. But your balance of the tokens is something which is stored in the permanent account storage. So it's called storage. So whatever you write or read from, whatever you write to this, it will stay over there even in the next transaction. So for example, your balance is being used in your future transactions that you do a few days later. So the balance will be there, but the stack and memory will obviously be deleted. And so there are these three things uh, in the EVM. And one extra thing is the EVM code, which is so every account has some so when we deploy a contract on Ethereum, so we can sorry. So in one example, we will see that how to deploy a contract by writing EVM code, and in that we basically return some values. Uh, yeah, in that we return some value, so that value is stored in the this EVM code. So EVM code is basically contract bytecode. So so whenever we deploy a contract on the blockchain, so that code has to return some value, that this is my code, and then it is stored here and it cannot change. But there is one so in 2018 a new feature was introduced in the Ethereum blockchain, actually in the EVM. It's called create to. So that allowed to actually change the EVM code. So that is one thing just I wanted to mention, that though it is written here that it's immutable, but actually because of that feature called create to, which was introduced in 2018, so this is actually not immutable. So yeah, so now this four things are there, and there is one new feature called transistor storage, which is in the discussion that it will be added. So it's not yet finalized that it will be added or not, but many people are supporting that feature, so that one extra thing will also be added to the EVM. But for now, we have this thing, these things. So now this was just some basic introduction that we went through. Now we can actually go through how we can actually use this EVM. So I just have one tool from which we can run EVM code. So for example, I just want to try an example in which we are adding two numbers. So so in order to add two numbers, we have to use add opcode. So we can go to the reference. So in this link, there is this second link, which is the EVM opcodes. So here you can see the first opcode, second opcode. So this opcode is add. So what it says that this opcode, so it needs just two inputs. So it pops the first integer value, a second integer value from the stack, and it pushes this value on the stack. This is the a plus b mod 256, 2 to the power 256. So now we are just going to see an example how we can use this add opcode. Uh, can you guys see this other screen?
Yeah, we can see.
Okay. So we want to use this add opcode. So this add will pop two values from the stack. But right now, if we start the execution of this code, there is nothing on the stack. So we will need to push something on the stack. So there is one opcode called push one. So using push one, we can push something on the stack. So let's say we are pushing 3 and then we want to push 4. And then once this is done, then stop the execution. So this is just to explain this instructions again. So what will the Turing machine, basically this EVM will do is first it will look at this push one. So push one, basically push one byte. So push one, push one means I'm supplying one byte. So take this one byte and push on the stack. So it will push 3 on the stack, and then it will look at this push one, and then it will take this next 4 as well. So push 4 on the stack and then add. So now let's see what this does. So the push one was executed and it pushed 3 on the stack. And the second push one pushed 4 on the stack. Right. Wait, this is an old version. Yeah. So yeah, first there was nothing on the stack, and we run the push one. Basically, this 3 we pushed on the stack, and now on the stack we have 3, and again we pushed something. Basically, we pushed 4, and now we have on the stack 4 and 3. 4 is at the top, and below 4 we have 3, and now add. Sorry. So add, and now add will pop 2 elements from the stack. So it took out 4, it took out 3, and the whatever the thing the add opcode did, and the output of that operation 7, it pushed back on the stack. So this is one simple example which I think we also went through in our first semesters. It is similar to the MIPS thing we did. So just like this add opcode is there, there are more opcodes here. So you can see multiply. So we can just multiply. So 4 into 3 would be 12, but these numbers are actually in hex. So that's why it's showing C on the stack. And then, yeah, there are more methods. So right now, in our example, what we just saw was how the stack would be working. I mean, how just if we see at the program counter and stack, then how that looks like. And just to see the gas available thing, uh, so the opcode that we used is the push one and add opcode. So the add opcode uses how much gas. So it should be mentioned here. Yeah, it uses 3. So it uses 3 and we used push 1 as well. So we can see that push 1 also uses 3. So we did push 1 2 times, and add once. So it would be 9 gas consumption. And we also did stop, which should be 2. Yeah, now I'm actually thinking why the gas used is 11 and why it's not 9. So if this is costing 3, this is costing 3, and this is costing 3 as well. So it should cost 9.
It is showing 9 only. The
Oh,
multiplication one
yeah,
is
right.
showing.
Yeah, true. So multiplication is 5. Sorry. And when we did add, at that time it was 9. But in case of multiplication, since multiplication costs 5, so so yeah, in that case, 3 plus 3 plus 5. Uh, this is the gas. So in our example, we just saw how the program counter, gas available, and stack, just these 3 things would work. Now we can do some. Now we can include memory as well in our example. So we would now use this 4 things. So the memory is, there are 2 main opcodes for the memory. So mstore. So mstore just stores something in the memory. Let's just try it right now. So let us understand what it does as well. So mstore takes 2 inputs. So it needs an offset and it needs a value. So offset is basically location where you want to store in the memory. So the first thing is the location in the memory where we want to store, and the next thing is value. And always note that everything here is in 32 bytes or 256 bits. So the value that we have on the stack is 32 bytes or 256 bits. So this value C that we have here, or let me just use the add opcode so that we have 7. So now what we are going to do is we will store this value on the stack. So we will add some instruction here, that is the mstore. So mstore takes 2 arguments. So it needs a value. It needs a it needs an offset and a value. So value we already have on the stack, but before that, above 7, we also need the location on the stack. So let's say the location is 0. We want to store at the 0th place. So let us just push 0 on the stack. Oh, we also need to add the mstore. Yeah. So in our previous example, whatever we did, we just added 2 numbers, and then the the result was pushed on the stack. And on top of that, we also pushed this memory location, that is 0. So we just added one simple instruction to just push 0 on the stack. And now on the stack, we have 0 and 7. 0 is on the top, and below 0, we have 7. And then we use this mstore. So now mstore wants 2 opcodes. Sorry, mstore wants 2 values. It pops 2 values from the stack. So it first pops 0 and sees it as the offset or memory location. And the second thing that it pops from the stack is 7, which it sees as the value, and this is what it stores on the memory. So this is the memory location 0, and on the 0th location it is storing 7. uh, so this is the memory now. just to show what would memory location so this memory is in hex. So every two characters here represent 1 byte. So similarly, there are 32 bytes here, and since we just stored this 7, so you might be thinking why didn't 7 was saved here? Why it got saved so far? So that's because here on the stack it might be it might be appearing like it's just a 0, it's just a 7, but this is actually a 256-bit number. This is also a 256-bit number. I mean, its size is big. So though it's appearing like 7, just one, it is just taking one small space, but actually it's taking 32 bytes. So when you want to store it in the memory, or when the mstore stores it, so on the stack it's a huge number. So that's why it's taking this much space. So this way we have this value in the stack, and you must be seeing this thing written here as return. So there is this concept called return data in EVM. So this is also one kind of location which is actually not mentioned here. So though it's not shown here, just like this EVM code is one place, there is another place called return data, and it is also similar to how memory is. So it is also one place in EVM. So if we copy anything over there, then it's considered as the return data. So it would be mentioned here. And right now, let us try doing that. So we will just say that we want to return something, and to return something, there is one return opcode in. So its name is return, and basically in Ethereum contracts, whenever if you are familiar with functions, so if they return any value, so this is the opcode which is being used to return anything, and so we have to tell this opcode that so it will read from the memory. So we have to tell that start from this place in the memory and up to this much size. So let's say this is the memory and I want to return just this one single byte. Then I can do that. I can just say that start from the 31st byte and one size. So at the last, I can say that push. So since offset and size, so I will have to push the size first and then offset I have to push after that, and then I have to call the return, because if I push offset first, then it will go below in the stack. I want offset to be on the top when the return is being called, so I will push this later. So first I will push size, and size is just 1 byte, and the offset I'm pushing now, and offset is 31. So this is in hex, so I'm just saying it to be in decimal. So I'm just saying that this 31 is in decimal, and now this will, okay, I have to also include this return instruction. So yeah, now I hope this instructions make sense. If there's something which doesn't make sense, then please stop me and ask. So just to go through this thing quickly. So we just first did an add, and then we used mstore to store this result of the addition in the memory. So this is how it looks when it's stored in the memory. And then now we want to return this value. So we first computed the addition, then we stored that addition in the memory, and now we want to return that value. So then for returning the value, we did this thing. We said that start from the 31st byte. So these are all 32 bytes. So this will be the 31st byte, and from one would be the length. I mean the size. So let's see what it does. So it returned just this small byte, 1 byte, because our length was 1. We could also have returned, if we switch this parameters, if we just say that start from 30 and the size should be 2. If we said start from 30 and the size should be 2, then yeah, we would be returning this value. So you can see that this value is returned based on what we are saying to the return. So is there any question with or any doubt which doesn't, anything from this which doesn't make sense? Feel free to just ask. So now we will just see one quick some of the examples. So we just saw an addition example, and there are a few more examples. We can just have a quick look over them. So if we want to see get a square of a number, then so this call value would just give how much value is being passed, and it will push that on the stack. And duplicate one is an opcode which just duplicates whatever is just above, just on the top of the stack. So imagine you passed in 3. So 3 would be pushed on the stack. Duplicate would make it one more 3. So there are now 2 3s on the stack. Just and then multiply. It would multiply that, and you would have 9 on the stack, which is the multiplication of 3 into 3. Then push 0. Then mstore, basically storing this result of the multiplication in the first memory slot, and then just returning it. So we can just try this example. So here we pass the value as 3. That's why you can see when call value was called, then I mean that was used, then 3 was pushed on the stack, because we passed the value as 3, and eventually 9 was returned. So while returning this, you can note that this was started from 0 and the length was 20 in hex. So these numbers are actually in hex, but in decimal it would look like 32. So 20 is 32 in decimal, so 32 bytes. So return 32 bytes. And yeah, so now if you wanted to see, so similarly we can write more code. There are a lot of opcodes which are available here, and with different combinations you can just write any amount of any kind of code. And uh, the the important thing which makes EVM as a Turing complete language, a Turing complete machine, is the jump, these kinds of opcodes. So jump basically helps to implement loops. So I think you guys are familiar with that from the MIPS class, but just mentioning it again. So in Bitcoin as well, there are these kinds of opcodes in Bitcoin script. But the only difference we can say, which adds power to the Ethereum side, is ability to basically jump into different basically move the program counter to somewhere else based on conditions. So you could implement loops. And when you can implement loops, you can just add very diverse kinds of logic in the code. So yeah, you can so there are very different kinds of code which can be implemented. So this is one example of checking whether a number is a prime number or not. So this is one example which I tried like 2 months before when I was trying to understand this thing. So you can just implement the code and based on the input. So if you just want to see this running once, so 2 is a prime number, so it will return 1, basically true. And if you pass in something which is not a prime number, then it will return 0. So it just does some logic. I just use very basic logic that it just keeps on. Yeah, I think it just does a for loop to find out whether it's a prime number or not. So the main thing which helped to write this code was this jump instruction. So so there are multiple jump opcode used here. So it actually allowed to implement loops in the code, and that's what adds gives a lot of power to the code writer. And yeah, one can write a code that does a lot of things in less space. So this takes less instructions, but it can find a prime number for even a bigger number, although it would be very inefficient, but still. So this is for some simple programs. So if one wants to deploy contracts, so this is some examples for deploying contracts. So this is one example which deploys a contract with FF as a code. And so yeah, you can write these kinds of code. And now just moving to Solidity. So the real contracts which are there on the blockchain, how their code looks like. So when we wrote this code, uh, for example, we wrote the code for, yeah, when we wrote this code, then the bytecode looked like this. So this is the bytecode for the EVM code which we just wrote. And now we can just go and see what real world contracts look like. So if you just go on the Etherscan and go into any random contracts, for example, this is the contract. This happened to be the SHIB token, but anyway, okay, the bytecode, I'm not sure if they show it here. Yeah, so this is how the bytecode looks like. So it's a lot of code. And okay, it's the creation code. So we can just take this code and run this code in our in this place. So the creation code, whenever we want to create the contract has to return. So just like we return this value here, the creation code has to return the bytecode. So just like this is so I just paste this thing and I'm going to press enter. So there was a lot of execution that took place. So a lot of and you can see a lot of memory was also used. Okay, finally this thing went out of gas. So I have to provide more gas. So I'm just passing gas limit as something very huge. Yes, now we can see that this much gas was used, and the returned code is this code, which is returned and stored into the contract's code size. I mean, in this architecture diagram, this part EVM code. So whatever that is returned, that is stored as the EVM code, which is here. And yeah, I mean, we don't always have to we don't mostly have to write EVM code. So people use languages like Solidity or Viper, or even there are some more languages which allows you to write uh, code in control flow kind of statements, if else kind of statements, which are more readable and easier to debug. And people don't really have to write code in opcodes or in this kind of way. But yeah, if someone understands how this works on a lower level, then it helps them to understand how things work on a higher level, and maybe write a better code or understand things.
Hello, Soham.
Hello. हाँ भाई.
Yeah. So I had a question. When we write the contract in Solidity, so the
Yeah.
contract which is deployed on the blockchain, is it only the bytecode which is being deployed?
Yeah. So it's just the bytecode which looks like this.
That's all.
Yeah, that is deployed. So even if you zoom into this and see, so 60 is pushed, 80 is a value which is being pushed on the stack. So again, 60, 40. So 40 is again pushed on the stack. So these are just the bytecode. I mean, these are just the opcodes which are there. So push one means 60. I mean, you can
So
see
even if we write a contract in Solidity or any high-level language, so it will get converted into those bytecode, and those bytecode will be deployed.
exactly,
So instead of writing Solidity, I can directly write the bytecode if possible.
exactly. So you can write the bytecode. Just the thing with that is, if you want to implement complicated logic, so it is. I mean, it is confusing sometimes, because when you want to implement loops, so one of the issues that, for example, I stumbled up with. Uh, so, for example, writing this prime number code. So, so sometimes you want to say that if this condition is true, then jump at this location. So you have to continuously update the location whenever you're writing, and Solidity basically handles all those things. I mean, if you are writing the bytecode by yourself, then whenever some condition is true, so for example, if I equals 1, then finish the code and return true or something like that. So you want to say that just jump to the end of the code. So this is at the end here. So imagine you added some code here, you added more things here. So this value would change, right? So it's sometimes it gets. I mean, most of the times when you're writing complicated code, then it's difficult to keep on updating it. But there are some new languages. I mean, new tools. For example, ETK. So some tools are there which enable to write this kind of code and add some alias over there. So this is also something which can be used. So this is just one extra layer over the EVM bytecode. So instead of directly writing EVM bytecode, one can just write this kind of code, which is compiled into bytecode. So you can see some layers. So one is bytecode, and then this mnemonics kind of way using ETK, and then a higher level would be writing Solidity, and even Solidity has a lower level thing called U. So one can write some code that looks like this. This is also very low level, but yeah, I mean, this is also converted into bytecode. But if you want even more abstraction, even more higher level, so then you have the Solidity. So then this kind of code can work.
Okay.
Yeah. So the goal of this call was just to give an introduction to how this thing works in low level, because to be honest, I was also curious about this for years. I mean, I wanted to understand how this works on a lower level, because then it gives some understanding of how we can do the higher level things better. Because if we don't know the some of the lower level concepts, then we might
Hello.
take bad decisions.
Hello, Soham.
Yeah, bro.
The language which you are using, that is not the Solidity also, and that is like assembly language, right? So what
Yeah.
is that language is called? That is not the bytecode also.
Yeah, you can call it mnemonics. I mean, not the private key mnemonics. So, so actually, this is just some different representations. So, for example, we want to use add opcode. So we would be using this 0 1, but instead of that, we are using add. So that's why this. So on this website, it's called mnemonic.
Mnemonic language, acha.
Yeah, I
Okay.
mean, you can call it that. So
Okay.
there are different ways, there are different options to write bytecode. So bytecode is directly, which looks like this, and solidity is there, then Yule is there, and mnemonic.
So I have one more doubt. When we deploy a smart contract on the blockchain, so on the blockchain only bytecode we can anyone all the other people can see only the bytecode, right?
Yeah,
So that from that bytecode, can we just that can we get the reverse of the what is that code is and all?
yeah, we can attempt to decompile the code, because if you just look at the bytecode, then you can just understand the logic, right? So this code is
Huh?
just pushing uh, s- things on stack, basically storing a 42 on location 0 and returning that. So you can see this and understand the logic, what's happening. But and then you can build some tools which understand this logic, understand the compilers, how they compile the code and decompile it. So right now there are some tools on Etherscan which help to decompile bytecode. So you can see this decompile option here.
Okay, click in that. Huh.
Then it does some decompiling, but it's sometimes it's not that much readable if optimizations are being used in the compiler. So you can somewhat see that, okay, this is one function called approve, and then there is this if condition, if not caller, then do this reward. So yeah, it's somewhat readable, but you will not get exact source code, right? But you should be able to get something that's fairly understandable, that you can
Okay.
understand the intent of the code.
Okay.
But yeah, that is only possible if it's compiled with a standard compiler. But if someone has written the assembly code with their bare hands, for example, writing custom code, so it might not follow standard. Hence, the decompiler might not be able to do the decompilation. So yeah,
Okay.
that is
Saying that, I mean, uh, when we deploy a contract, so from that bytecode, sometimes we cannot able to understand what that contract is. That's what, right?
yeah. So it is possible
Sometimes
that someone,
it's not possible
yeah,
to
sometimes
understand.
it's not possible. And the cases when it's not possible, when someone has written very complicated, I mean, they have used some non-standard compiler,
Mm-hmm.
and if they are using optimizer runs, I mean, more optimizations, so that uses some that changes some bytecode, adds some things in the bytecode to make uh, more optimizations. Or there is also this concept called code obfuscation. I'm not sure if I'm pronouncing that correctly, but you get the idea, right?
Yeah,
So,
yeah.
The one normal logic is there, and you just add a lot of garbage in there, and it then becomes very difficult to understand for you human. But when that code is run by a computer, then yeah, that garbage logic is also run, but finally it cancels out, and the output of the code is basically the same thing.
Okay.
Hello.
Hello.
Yeah, I had a question. In the like when we are writing smart contracts, there is a concept of like packing of variables, right? I mean, to reduce the gas prices. So what actually happens? I mean, under the hood in the stack.
Yeah. So that packing is done for the storage. So here you can see the stack is there, memory is there. So these are fairly cheap in comparison to storage. So storage is hundreds of times costlier than memory. So to reduce the cost, so every storage slot is 32 bytes. So if you have something like very small numbers, so what you can do is instead of storing those numbers in separate slots, they can be stored in the same slot. Let me just try to find one quick example. Or yeah, I know where we can see. Sorry. So this is one example of a contract where you can see there are a lot of variables. So, but all of these variables are stored in a single slot. So one slot is 256 bytes, 256 bits. Sorry. So this is 160 bits, 24 bits, 16 bits. If you add them up, and this boolean is 8 bits. So if you add them up, then they all are in the single slot. So this is then you can call this as a closed packing of variables, and this is done for storage purposes.
Okay.
So yeah, now just if there are more questions, then please ask. And just for further reading, you can have a look at this site, and there are some more links how this thing works on more deeper level, or there are some links which explain uh, some dependencies of this thing, like more things linked to the EVM. So you can find a lot of things mentioned in this link. Yeah, and I've also mentioned one EVM puzzles link, which is the last one. So if someone is interested to just try some easy examples, easy puzzles, so you just have to write a small EVM code, which so this is just one small game, or you can call it as a puzzle. So it will give you around 8 or 9 problems, something, and each problem will you have to logically solve the problem and come up with a bytecode, and basically type that bytecode and press the enter button. Then if that is a correct solution, then you would go on the next level. So yeah, this is one really nice exercise if someone would like to try that. So yeah, that's pretty much it for the today's call. And yeah, I hope we do more calls uh, in the coming weeks. Any last closing
Yeah,
questions?
so like where is the address of the smart contract has been added in the bytecode?
Uh, okay, when the contract is being deployed.
Yeah, yeah, yes, yes.
So yeah, I mean that address is not included. So depends depending on if create is being used. So if a normal contract is deploying the normal address is deploying the contract, so the contract is deployed at an address which is calculated. So just a second. Yeah, it's deployed using one calculation. So it's a hash of the address and nonce. So let me find.
Like,
Yeah, you can just
like
Google it.
won't that be showed in the bytecode? Like, or
No,
like whatever the whips are like.
no, that's not added to the bytecode.
Oh,
So that
okay.
address is when you deploy the contract. So it's deployed at an address. That address can be computed using this logic. So it's just the check hash of the RLP.
Yeah, that's fine. But okay, it won't be showed in the bytecode
No,
while running.
it's not shown in the bytecode.
And what if one contract is calling another contract?
Yeah, in that case, you would need to have that address of the other contract in the contract that is calling. So now there are various ways you can supply that address to the contract. You can include that in the bytecode, or you can just pass it in some future functions, or you can store it in the storage. So self address is not necessary to store. I mean, it's not stored, but yeah, if you want to call someone else, so then you will need the address of that other contract somehow. Either you supply it in your in the self bytecode, or supply in the parameters of the self. Just as a quick example, here I just want to see a balance of something. So I have to pass it as a data here. So this address is passed as a data. So I could include this address here in the bytecode, or I just passed it as a parameter. This is called the call data. So does this one make sense? Yes, so I would request you guys, I mean, those who are interested to see this thing further, to try these puzzles. So yeah, I mean, this will take around uh, 15 to 20 minutes, or max 30 minutes. Uh, yeah, it's an interesting exercise. And after, so before doing this EVM puzzles, I really didn't have much idea of how this works. But after doing these puzzles, I was very much confident on how this works. And yeah, I also have some examples. So this code which is there, it is available in this second last link. So you can just go here and you can find the things in this example. Yeah, so that was, I think, pretty much it for the call. And is there something more you would like to ask before we wrap up the call? And yeah, the I'll make the recording available, uh, maybe on the YouTube or Google Drive somewhere. So if there's nothing more thoughts to add, then we can just wrap up the call for today.
Yeah, okay.
And then thanks guys, thanks for joining. And yeah, if there are any questions you come up in future, then just feel free to post on the group, or feel free to DM.
Yeah, thank you.
Okay, thank you.